you must have seen that, or you must have noticed that this Newman projection is easier to represent on a paper as compared to the earlier projection methods, isn't it? Now, how to locate or how to exactly express the conformation of a molecule using this Newman projection, that we will see here. Now, for this, let us replace the simple I symbol with a fellow. Okay, as I told you earlier, Newman projection, whenever it is drawn, we have to show the plane from which the structure is observed, and how it is shown in the two-dimensional paper by using or by drawing an eye, is not it? Now, what happens? Suppose now see, instead of using an eye symbol here, we can replace the eye symbol with that of a boy. Okay. Now, if we do that, what we can observe here is, see, this right hand of the boy is pointing towards the chlorine atom, and his left hand is pointing towards hydrogen atom. Okay. Likewise, the methyl group is pointing straight down. Is not it? That is all there is that we can say about the first carbon. Is not it? So we can say here the boy is looking through the C1-C2 bond from top left. Clear? And the structure can be represented by using Newman projection like this. If this Y structure is a representation of the boy, in that case, his left hand is pointing towards hydrogen. Right hand or right hand side, we can see the presence of chlorine atom, and straight down we can see the methyl group. Isn't it? Likewise, we can also compare the position, or we can exactly locate the position of OH group, H group, and Br group. Isn't it? And how we can locate the position of the functional groups or atoms attached to the second carbon? Let us see that. On the second carbon, we have an OH group which is pointing straight up, and a bromine atom which is pointing down. Okay. Now here we can see, if we try to imagine this boy and the location of his right hand and left hand with the position of these three functional groups, we can see on the second carbon we have an OH group which is pointing straight up, a bromine on the bottom left, and an hydrogen atom on the bottom right. Now, this presentation, or this way, we can say Newman projection can be better represented as compared to representing an eye. Instead of using an eye symbol, if we take the imaginary humanoid picture. In that case, it helps us to understand the Newman projection better, or it helps us to predict the Newman presentation in a better way. Projection, by using this Newman projection, a single molecule can be shown in various ways. Now let us see what are the various ways. Now in the earlier diagram we saw, or in the earlier example we saw, the boy is looking from this angle. Now what we have done, again the boy is observing the molecule. However, his angle of observation has changed, as I have specified, or as we have already studied earlier. Newman projection is based on the direction from which the molecule is observed. It is always based on the direction from which the single bond is observed. Now here the angle of observation has been changed, is not it? Now depending on the angle, the Newman projection of a given molecule may look completely different. If the boy looks the molecule from this side, the molecule will look different. And if the boy tends to look the structure from this side, again the structure or the molecule will look different. For example, if we want to look through the C1, C2 bond of the previous molecule from the bottom left, that is what we will get here. Let us see what we can get here, or how the Newman projection of this structure will look like if at all the boy is observing the molecule from this side. Okay, now if we see towards the right hand side of the boy, bromine group is present, and towards the left hand side we can see the hydrogen atom, whereas the OH group is pointing towards the head of the boy. Okay, so if this is the representation of the boy, in that case OH group is facing up, hydrogen atom towards the left hand side of the boy, and bromine atom towards the right hand side. Now, keeping the boy same, we can find out which functional group of the second carbon lies towards the right hand side of the boy. Here we can see, if we see the hydrogen atom is lying just behind the bromine atom. Behind the bromine atom, you can see the presence of hydrogen atom. Now, how we can say that? Because in both the cases, let it be C1 or let it be C2, in both the cases, bromine and hydrogen, they are represented by using dash bond, isn't it? Which indicates that these two attachments are lying towards the bottom. And if we try to correlate that these two positions represent the same thing, then we can say hydrogen lies towards the right hand side of the boy. Here we can see the round symbol represents the carbon at the back end. Okay. The second carbon, the back end carbon is having hydrogen towards its right hand side, and to the opposite, means if downwards we can see hydrogen atom, towards the upward direction we can see the presence of chlorine atom. So hydrogen and chlorine, they are lying just opposite, on the opposite sides. Okay, if hydrogen is towards right, chlorine is present towards left. Next remains the CH3 group. CH3 group is present towards the bottom. Here we can see the presence of the CH3 group. This way, we can say if the angle of observation is changed, the molecule may look different in Newman projection. These two Newman projections represent the same compound, which we can confirm by flipping one of them by 180 degree through an axis. So how can we know that both the structures are the same? It can be confirmed only if we rotate the structure by 180 degree. Now see the second Newman structure. This was the second Newman structure. Okay. It had bromine towards right hand side, hydrogen towards left hand side, and OH towards its top. Okay. If we rotate this molecule by 180 degree, then what will happen? What will happen? What and all changes we can observe? This bromine will move towards this place. Okay, see here we can observe clearly that the bromine which was lying on the right hand side, because we are rotating the molecule by 180 degree. So right will go to the left and left will come back to the right position. Observe the changes? Yes. Now apart from bromine and hydrogen, this molecule is also associated with one substitution called OH group. Now, when we rotate this by 180 degree, you just think of a structure, say, we have got a scale-like thing. You just imagine we have got a scale-like thing, and to both the ends of the scale, we are having three attachments, just like the three functional groups. Okay, now if you rotate the scale by 180 degree, what will happen? The end which was initially staying away from you will come towards you, and the end which was earlier lying towards you will move away from you, is not it? अगर हमारे पास हम एक स्केल लाइक स्ट्रक्चर लेते हैं और एज्यूम करते हैं कि वो स्केल जो है वो कार्बन कार्बन सिंगल बॉन्ड को रिप्रेजेंट करता है, ओके, आणि that scale like structure is associated with three functional groups or atoms. Now if we rotate the scale by 180 degree, what will happen? The end which was earlier facing towards us will move to the back, and the back end will come to the front. Okay, here we can observe that thing. Here see the Y structure, that is the carbon at the front is bearing the OH group at the top. When we rotate the structure by 180 degree, here we can observe the round symbol or the circle is showing the OH group at the top. That means the molecule got rotated, or that carbon-carbon bond got rotated by 180 degree. Okay, so with this we can say one structure can be converted to another structure by Newman projection very easily. One thing you must notice here is that the template pattern for the two Newman projection is somewhat different. In the first one, the front carbon has the Y shape, while in the second one, it is an upside down Y. Okay, now when we see the earlier Newman projection with the first compound and next the flipped compound, what we observed, the first carbon was associated with a Y like this, whereas the second compound was showing the first carbon in an inverted Y shape, is not it? Or we can also call them as front up and back down. Likewise, front down and back up. Okay, here front is down, back is up. Here front is up, back is down. Okay, so in both the cases, let it be the first carbon or let it be the carbon at the back, whatever is the situation. In both the cases, the carbon atom is associated with 3 substitution in an Y-shaped manner. Okay, of these three substitution associated with the first and the second carbon, the only difference is that here we can see the first attachment to the first carbon are oriented in a Y-shaped manner, whereas in the second case, the 3 substituents are oriented in such a way that they look like oriented in upside down Y pattern. This simply depends on the zigzag pattern. And if you visualize placing a model with open arms instead of a simple eye, it will make you or it will help you to easily find out the correct pattern. Okay, so one thing here we can remember is that there is no correlation as to wedge group on the zigzag is always on the right or a dash group is always on the top. Okay, with the earlier notations or with the earlier ways of projection, we observed that a dash bond always shows that indicates that the group or the atom is lying away from the observer. When we used to take a solid bond, it indicated all the times that bond is directed towards the observer, is not it? So if we talk about Newman projection, there is no question of confusion. Dash bond is representing this, wedge bond is representing that, or solid bond is representing this or that. There is no confusion like this in case of Newman projection. Now, you just think of a situation. Suppose there is a dog. Okay. Now this dog is observed by a person from this angle and a person from this angle. Okay. Just because the dog's tail is on the right does not mean it is always a correct statement. Okay. For this man will say that the dog's tail is on the right hand side. However, if at all we want to see the same object from this person's purview, then what we can observe? We can observe the opposite thing. So it is all that it is dependent on the direction you are looking at the dog. So if you change the direction from which you are looking at the dog, then we can observe one thing, that the position of the dog's head and tail, that will change. If we are seeing it from this side, you can say the dog's tail is towards the right, and from this person's purview, we can say that the dog's tail is on the left. Staggered and eclipse conformation. This is the new concept that we are going to see here. Along with the staggered and eclipse conformation, we will come across a new term called dihedral angle. What is dihedral angle? Now let us take our molecule and do a 180-degree rotation of the first carbon around the carbon-carbon single bond. What we are going to do? we are going to take this structure and we want to rotate this molecule. When we want to rotate this molecule by 180 degree, what will happen? The group at the bottom will move to the top and the group at the top will move to the bottom. And the group which was lying at the bottom will move towards the upper side. Isn't it? So similar, the changes after 180 degree rotation will be like this. Okay. See, you can see the position of Cl and H interchanged. CH3 was down, it has come up. With this unit also, we can observe the similar change. And now let us draw the Newman projection, still looking from the top left. Okay, we are observing the molecule from top left. Okay, if we want to observe the structure like this, in that case, what we can see, the CH3 group is towards the head of the buoy, whereas the Cl group is towards the left-hand side of the buoy, and the right-hand side is towards the hydrogen atom attached to carbon number 1. So when we represent this molecule by Newman projection, the first carbon will be represented by using a Y structure. Okay. In this Y structure, the CH3 group is moving, is shown up. It is present towards the upper end. So the first Y will be an inverted Y, and the carbon at the back will be represented by a imaginary circle. Okay, to this circle we can see the OH group is attached on the same side as that of the chlorine, whereas bromine is attached to the side same as that of hydrogen. Bromine and hydrogen placed on the same side, chlorine and hydroxyl group present on the same side, and towards the top we can see the presence of H atom. Is that clear? Newman projection pattern is clear for you?
Yes, ma'am.
Okay. Here what we can notice is that all the groups on the back carbon are exactly behind the groups which are atoms which are attached to the carbon at the front. So they look like as if they are aligned. This is called as the eclipsed conformation. For the sake of or for the ease of understanding, let us imagine a queue of students of same height. Okay, and they are standing exactly behind each other. They all are of equal height and equal health. Okay, then what will happen? Can we see them all? हम सबको देख पाएंगे क्या? नहीं, क्योंकि एक के पीछे exactly दूसरा आ जाएगा. Okay, and we can say they are standing aligned. If in a molecule where 3 attachments are attached to carbon number 1 and carbon number 2 respectively, in that case, when they are aligned in such a way that the atom which is attached to the front carbon and the atom which is attached to the second carbon, they exactly lie behind each other. In that case, we cannot see the groups at the or atoms which are attached to the carbon at the back. Now, we want to show all the attachments. So, for the ease of representation, what we do here is, instead of showing exactly behind each other, we just keep a small gap show the group at the back. Here we can see chlorine is at the bottom, hydroxyl group is at the bottom. Okay, front carbon is having chlorine. So chlorine is at the top, the front carbon, and the OH group is exactly at its back. Here we can see the similar type of positioning of hydrogen and bromine atom. Okay. Here it is representing an eclipsed alignment. That means carbon at the front and carbon at the back. They are oriented in such a way that the groups attached to the first carbon and the groups that are attached to the second carbon, they lie exactly in front of each other or back to back. In other words, the angle which is present between each eclipsing group, here chlorine and OH, they are representing eclipsing group. Then what will be the angle between chlorine and hydroxyl group? If they are exactly behind each other, what will be the value of this angle? The value of this angle will be 0. Okay, in such a situation, that is in eclipsed conformation, the dihedral angle of the groups is called 0. Okay, so what is dihedral angle? Dihedral angle is the angle between these groups. Okay, which groups? The groups attached to carbon number 1 and the groups attached to carbon number 2. See, if you observe this two structure, they are again representing eclipsed conformation. Here we can see back to back, back to back, back to back orientation of the attachment. Hence, dihedral angle between these two groups is 0. Dihedral angle between these two groups is 0. Likewise, dihedral angle between these two is also considered 0. So with this, I wish the concept of dihedral angle is clear. Now, notice that the dihedral angle in all the Newman projection we did earlier was 60 degree. हमने क्या दिखाया था? The carbon at the front was in one position, it was shown with a correct Y-like structure, whereas in the second diagram, see, here. Okay. Here the Y is oriented correctly, and here the Y is oriented in an inverted way, or it is invertedly oriented. In this two structure, what is the value of dihedral angle between similar functional groups or atoms? Here the dihedral angle is considered to be 60 degree. And how we can say it with that much confidence? It is because the entire round is representing 360 degree and there are total 6 divisions. So individual is having 60 degrees value. So in such type of structure where the position of the atoms or groups attached to the carbon at back and the carbon at the front, they are oriented in such a way that the dihedral angle is 60 degree. They are not exactly placed back to back. So we could recap that the dihedral angle in all the Newman projections we saw earlier was 60 degree. It was bisecting the group on each carbon all these conformations were staggered conformations. When the dihedral angle is found out to be, or the dihedral angle is 60 degree, then we call the conformation as staggered conformation. If dihedral angle is 0, we call it as eclipsed conformation. Whereas when they are having a dihedral angle value of 60 degree, we call them as staggered conformation. Okay. Staggered conformations are considered as the more stable conformations than the eclipsed conformation. And why? It is because the atoms like space, and the closer they come, they become more unstable. Here, if these two groups would have been present back to back, in that case, there would have been some interaction between these two. Okay, as a result, the space is because the space between these two groups becomes less, the molecule become unstable. However, when the angle between these two groups or these two groups or these two groups, any two groups, they increase, then what will happen? The stability of the structure change. When we talk about this dihedral angle, then it is assumed that we are considering the angle between the atom and the atom which is attached to carbon number 2 or carbon at the back, and the groups which are attached to the carbon at the front, to the front end carbon atom. Depending on the dihedral angle between the two larger groups on the staggered conformation, they can be classified as anti or gauge conformation. Now, what is this gauge and anti conformation? Let us see in detail. Now, let us say a structure is like this. Here, this is representing the carbon at the front, and this one is representing the carbon at the back. This carbon is associated with 3 functional groups. One is shown in red color, second and third. Whereas carbon at the back is associated with substituent like this, and this is the back end. Okay. 2 Y-shape structure we can observe here. Here, the dihedral angle, the groups which are attached to the front carbon and second carbon, they are oriented in such a manner that the dihedral angle is considered as 60 degree. They are away from each other by 60 degree. However, when we talk about anti-conformation, it is assumed that this red functional group, it gets oriented in such a way that it comes to this position. So here we can see the front Y and the back inverted Y, and how they are placed relative to each other. They are having 180 degrees difference between them. So we can say both are representing staggered conformation. However, here in gauge conformation, the dihedral angle is 60 degree, whereas in anti-conformation, the dihedral angle is 180 degree. A very good example is taken here. Here we can see the structure of butane. The carbon at the front is associated with 1 CH3 group and 2 hydrogen atoms. The carbon at the back is also associated with 1 CH3 group and 2 hydrogen atoms. Carbon at the front is shown with a Y, inverted Y structure, and carbon at the back has straight Y structure. And the relative position or dihedral angle between the adjacent groups is 60 degree here. If it is 60 degree, we call the conformation as gauge conformation. If we orient the structure in such a manner that one of the CH3 group lies at the top, whereas the second CH3 group goes to the bottom. If we rotate it, in that case, what will happen? We can see that the CH3 group, they remain away from each other. As a result, the structure gets a conformation like this, or this conformation where dihedral angle is 180 degree, and this conformation is called as anti-conformation or anti-conformal of butane. Of these two structures, which one is considered as more stable? One which is having more energy is less stable. One which is having less energy is more stable. जहाँ पे दो सिमिलर ग्रुप्स या दो बड़े ग्रुप्स एक दूसरे के पास आ जाएंगे, वहाँ पे इंटरैक्शन दो ग्रुप के बीच बढ़ जाएगा. It may be steric hindrance or it may be any other type of interaction. When there occurs any sort of interaction between the adjacent group, what will happen? The molecule tends to become, or the conformer tends to become unstable. When there is lesser interaction, we can assume that there is more stability. So of these two structures, which one is supposed to have less interaction? Here they are closer, so more interaction, hence less stable. Here lesser interaction, hence they are more stable. This one is less and this one is more stable. Now let us see what is energy diagram. Before we go to the explanation of energy level diagram, now till now we have studied that, or we have learned that a particular molecule can be shown in various conformations, and all these conformations are interconvertible. Okay. Now when we talk about various conformations, all the conformations are associated with different amount of energy. Okay, if we try to plot, or if we try to represent the energy level of all these conformers in a graphical way, we call that graph, or we get an energy diagram. Okay. We will start the energy diagram with the various conformations of butane. In order to understand how the transformation from conformation to another, one conformation to another occurs, let us imagine holding the front carbon steady and rotate the back carbon by 60 degree. Of course, in reality, they both rotate. However, we only do this to make it easier to visualize. We could also keep the back carbon steady and rotate the front carbon. Okay, so we can find out all the conformations of butane by doing this imaginary rotation of one of the two carbons. Now, if we rotate, see, let us start the first structure of butane with an orientation like this. Here we can see CH3 and CH3. They are lying opposite to each other, and the dihedral angle is supposed to be 180 degree. So we can say, if we draw a graph taking energy along y-axis and dihedral angle along x-axis, what we can observe, the first and this orientation, that is anti-conformation, is supposed to be associated with less energy. This lesser energy is associated with higher stability. Now, suppose we were keeping the carbon at the front stable, we want to rotate this. the attachments to the second carbon. So what will be the first change that we can observe here? The CH3 group goes exactly back of the hydrogen. Here we can see CH3 goes back to hydrogen. This H will go behind CH3 and this H will go behind this H. If that thing happens, then what we will call it as, this type of conformation is called as eclipsed conformation. Here the interaction between the adjacent group is more, so they are supposed to be less stable when this orientation or conformation is associated with more interaction. It is supposed to have lesser energy. As a result, we can see here interaction and the energy level. Now if we keeping the carbon at the front same, now if we further rotate, what will happen? Again there will be a dihedral angle of 60 degree. However, here what will happen? Now this hydrogen will move to this position. The next hydrogen will move to this position and this CH3 will move to this position. Okay. Here, as because the stability of this structure, because of eclipsed conformation, it is less, hence energy of this eclipsed conformation is considered more. Energy here is less, so it is more stable. Here interaction is more, as a result there will be lesser stability and energy will be more. Is not it? Energy and stability, they are inversely related to each other. Here, after 60 degree orientation, what we can see? A structure like this. This structure is considered as a gauge conformation. Here we can see the dihedral angle between all the substituents is 60 degree. Upon further rotation by 60 degree, what we will see, CH3 goes exactly behind CH3. As a result, the extent of repulsion between CH3 and H, or extent of interaction between CH3 and H, is supposed to be less as compared to interaction between CH3, two CH3 groups. So there will be more steric hindrance. As a result, it will be even less stable. Hence, its energy is considered even more. Upon further rotation, this CH3 will move towards this direction and it will come towards the right hand side of the CH3. And now we have to place the CH3 groups at 60 degree. Now when this rotation takes place, or when this when we get an orientation like this, we can say this structure has got 60 degrees dihedral angle and it is considered as gauge conformation. However, when we achieve this conformation, the energy level or the interaction between these two groups will be lesser. As a result, it will become more stable, hence its energy will come down. Upon further rotation, the CH3 group will move to the back of H. As a result, there will be somewhat interaction between H and CH3 group. Here we can see the position, H and CH3 group lying back to back, H and H lying back to back, and H and CH3 lying back to back. Again, they are representing eclipsed conformation. Eclipsed conformation means they are unstable, hence they are having comparatively lesser energy. Upon further rotation by 60 degree, what will happen? This CH3 will come to this place. Okay, the CH3 will come to this place and we get a structure like this. Here we can see CH3 comes to the bottom and H and H, these two will lie like this. Okay, here we can say the anti-conformation has been achieved because the dihedral angle between the two larger group is 180 degree. When the interaction or when the distance between the larger group is maximum, the interaction between the larger group is supposed to be when distance is maximum, the interaction is supposed to be minimum. As a result, what will happen? The energy stability of the molecule will increase and the energy will come down. So as these conformations or this interchangeable conformation takes place, what happens? The energy of the molecule keep on changing, and in which way it changes, that is shown by this energy level diagram. This diagram is called as the energy level diagram of butane. Okay, here we can, if at all we observe this structure carefully, or if we observe this energy level diagram carefully, we can observe or we can come to a common conclusion that for eclipsed conformation, or all the eclipsed conformations are having more energy, hence they are less stable as compared to the anti and gauge conformation. The anti conformations are supposed to be structures or conformers with maximum stability, whereas gauge orientations also, or gauge conformers are also comparatively stable and their energy is less. Maximum stability, anti-conformers. Intermediate stability, gauge conformers. And stable conformation or more energy bearing conformation, we will come across various eclipsed conformation. However, when two larger groups are eclipsed with each other, that will be the conformer having highest interaction, as a result highest instability. Okay, and as because the stability becomes minimum here, the energy of the eclipsed larger group, between eclipsed position between two larger groups, is representing the highest energy bearing conformation. I wish the concept of energy level diagram is clear to all of you.
Yes, ma'am.
Now, the closer you put the larger methyl groups, the more unstable the conformation becomes, which is the same to say the greater the distance between the larger groups, the more stable the conformation is. Also, the larger the group, the more unstable the eclipse structure and gauge conformation. Here, notice that any staggered conformation, let it be gauge or let it be anti-conformers, both anti and gauge conformers are called as staggered conformers only, or staggered conformations only. Here we can come to a generalized conclusion that any staggered conformation is considered more stable than the eclipsed conformation, and gauge conformation, the staggered conformation is more stable than the more stable eclipsed conformation, and the gauge conformations are less stable as compared to anti-conformation. Gauge are less stable as compared to anti. However, staggered conformers are having lesser energy, that is more stability as compared to eclipsed conformers. These two rectangles they are representing eclipsed and staggered conformation. Within this larger rectangle, we can see both gauge conformers and anticonformers. Anticonformers are energy-wise minimum energy-bearing conformations, as a result maximum stability-bearing conformations. Eclipse conformations are supposed to have high energy level and hence less stability. The eclipsed conformation, where two larger groups are exactly behind each other, it represents the structure with minimum stability, hence maximum energy. Next gauge, next eclipse, next anti. Clear? Now let us learn what is torsional strain and steric strain. Now, why this interaction between these groups? They make the structure unstable. That is all because of torsional and steric strain. What is steric strain? Steric strain is related to steric hindrance. Steric hindrance is a broad definition and it occurs when atoms or groups are close to one another and there is an increase in energy because of the repelling electron clouds. This functional group is associated with its own electron clouds, and the atom or group at the back is also having its own electron clouds. When they come close to each other, the electron clouds of each other, they interact. As a result, what will happen? Electron-electron interaction. It is considered to be attraction or repulsion. Definitely, it is supposed to be a repulsion type of interaction. Okay. This repelling electron clouds or repulsion between electron clouds leads to lesser stability, that is increase in the energy of the conformation. The torsional strain, on the other hand, is specifically for the eclipsing groups. The increase in energy which is resulting from eclipsing groups on adjacent carbon is called as torsional strain. And in order for this to be considered torsional strain, it needs to be an energy increase of of small eclipsing group. Now, when we talk about HH interaction, HCH3 interaction or CH3H interaction, in that case, where we can have this torsional strain when there is an interaction between HH or CH3H, where it is considered to be higher in case of HH or HCH3. In case of HH, it is minimum, and in case of CH3H, it is higher as compared to this. Okay. So when we talk about eclipsed conformation like this, here there will be steric strain as well as torsional strain. Steric strain, it comes into purview because of the bulkiness of the group. Here, both the groups are bulky, they are larger groups. Hence, here we can observe the interaction, steric interaction as well as torsional interaction. Here, both are small atoms and they are in eclipsed orientation. So, this type of interaction is torsional. In between these two atoms, we can have or we can observe torsional strain. Here also, we can think of torsional strain. However, here we can observe both steric as well as torsional strain. I wish the concept of torsional and steric strain is clear. The interaction of two gauge groups is a steric hindrance. Here, you see. Now let us take the example. Here, the gauge conformations are less stable or they are associated with higher energy as compared to the anti-conformations. When in Gauge conformation, these two CH3 groups are present at 60 degrees angle. If we talk about anti-conformation, in that case, this CH3 and this CH3, they will lie opposite to each other, where the interaction or steric interaction is supposed to be minimum, when they lie maximum away from each other. That is CH3 at the top and blue CH3 at the bottom. Okay. Now, how from based on experimental studies, it has been observed that when HH eclipsing is there, the molecule or the conformer is having torsional strain of 4 kilojoule per mole, or the same thing can be expressed in terms of kilocalories per mole, that is 1 kilocalorie per mole. Similarly, CH3H eclipsing is associated with torsional strain of 6 kilojoule per mole. CH3CH3 torsional plus steric strain is associated with an energy of 11 kilojoule per mole. See, it is supposed to be almost 2 times of this. That is interaction between CH3H. It is showing torsional strain of 6 kilojoule per mole, but here it is 11 when there is steric as well as torsional strain. When two CH3 group are in Gauge orientation, then there will be only steric strain, and the value or the energy associated with this interaction is 3.8 kilojoule per mole. Now, based on this structure, based on this experimental value, let us see how we can find out the energy associated with each conformation. Now, let us calculate the energy difference between these two conformations of butane. Here, if we observe the first structure, the first conformation has got CH3 in Gauge orientation. As a result, what will be the energy associated with this interaction? CH3 Gauge interaction, it is associated with 3.8 kilojoule per mole. Okay, which brings destabilization. When we talk about this orientation, here we can see there is CH3H eclipsing. And how we can calculate the energy of this second conformation? There are 3 eclipsing pairs. First eclipsing pair, second eclipsing pair, and third eclipsing pair. Here there is HH eclipsing. Here CH3H, and here also CH3H eclipsing. So here what will be the net energy of this conformation? HH interaction, here we can see 4 kilojoule per mole. Now let us confirm. HH eclipsing is associated with the torsional strain having energy 4 kilojoule per mole. Second is HCH3 interaction or eclipsing. Here also HCH3, here also HCH3. Here we can observe HCH3 eclipsing is associated with an energy of 6 kilojoule per mole. So, because there are 2 eclipsing, hence 2 multiplied by 6 kilojoule per mole, total 12 kilojoule per mole. So, in all, we can say total 3 interactions are there, 2 here, 1 here. So, total is 12 plus 4, 16 kilojoule per mole. And the energy difference between these two is supposed to be 16 minus 3.8. Why 3.8? This here there is positioning of 2 CH3 groups at a dihedral angle of 60 degree only. So it will destabilize the molecule conformer. Okay. So this much energy is deducted from the stable structure, and we get a value of 12.2 kilojoule per mole. The lowest energy conformations of ethane is called as the staggered conformation. All of the dihedral angles are 60 degree and the distance between the front and the back carbon hydrogen bond is maximized. If we now rotate the front CH3 group by 60 degree in a clockwise manner, then the molecule is in the highest energy, that is eclipsed conformation. So we can say in eclipsed conformation, the energy of the molecule is highest and the stability is lowest. It is because here dihedral angle is 0 degree. Now, if we stagger the bonds slightly in our Newman projection drawing, because we can see all of them, even though we are seeing some dihedral angle, actually they are exactly placed back to back or in a single line, just for the sake of or for the ease of representation. There is a small gap shown between these two groups or these two groups or these two groups. However, practically they lie exactly behind each other. So dihedral angle is considered as 0. This brings the electrons in the front and the back carbon hydrogen bonds very closer to each other, and there occurs a repulsion between them. The energy of the eclipsed conformation is approximately 12 kilojoule per mole, higher than that of the staggered conformation. Clear? I repeat, the energy of the eclipsed conformation is approximately 12 kilojoule per mole, higher than that of the staggered conformation. Rotation then is not strictly free because there is a 12 kilojoule per mole energy barrier to overcome an eclipsing of hydrogen atoms. Likewise, the barrier is low enough. As a result, rotation is very rapid at room temperature. Okay, and it is so rapid that they can be interconverted at a rate of or on the order of 10 to the power 10 times per second. Whenever this rotation takes place, how much energy we need? Almost 12 kilojoule per mole. Okay, in order to overcome the eclipsing of the hydrogen atoms, which is very less and which can be easily overcome at room temperature. If the energy barrier is overcome, then they can easily get converted from one form to another form. At what rate they get interconverted? The rate of interconversion is 10 to the power 10 times per second. I think the time is up. We will stop here and we will continue with the remaining part, that is from conformation of cyclohexane in the next lecture. Okay. However, your pharmacology madam has been informed